Welcome, Mr. Sutton here, bringing you the Pre-Cal Honors 9-3 Extra Practice Number 4 solutions on algebraic limits of polynomial and rational functions. For this problem, we're trying to find the what the limit as x approaches 0 of this function over here is equivalent to. Now, you'll see that they care about this because if you plug 0 in right away here, cosine of 0 is 1, minus 1 is 0, so that's okay. But then we have sine of 0, which is 0. Squaring that gives us 0. We end up with 0 over 0, indeterminate, which is not okay. So they want us to rearrange this algebraically, trigonometrically, into one of these options. Okay, so to get started on this, the key is using some of your Pythagorean identities. Specifically, we know that sine squared plus cosine squared equals 1. So sine squared then could be rewritten as 1 minus cosine squared if we rearrange that identity. So I'm going to rewrite it like that. And then, let's see here, we're going to do a little factoring and canceling because we haven't really solved anything yet by just rewriting it that way. So I'm going to factor a negative 1 out of the numerator, giving me 1 minus cosine of x. And in the denominator, I can split this up into 1 plus cosine of x, 1 minus cosine of x. That's why I bothered rewriting the numerator. So those 1 minus cosine of x's are going to cancel, and that leaves us with just negative 1 over 1 plus cosine of x. Now you'll notice if you plug 0 in at this point, you end up with 1 plus 1 down here, which is not 0, and we didn't have 0 up here anyway. So this is a much better situation for us to deal with, and it also happens to be answer choice A. For this problem, we're trying to find the limit as x approaches 0 of this crazy-looking function. Now the key on this is that this function is comprised entirely of continuous functions. Cosine is defined everywhere, so is e to the x. In fact, e to the x is also positive everywhere. So we're pretty much guaranteed that we're not having 0 in either the numerator or the denominator. All right, so let's go ahead and just plug 0 in then and see what we get as a function value, because that's going to match the limit on this one. So plugging 0 in for all those x's, cosine of 0 is 1, and we've got 4 times 1, basically, so we're adding 4 up there. Down here we've got 5 times 1, which is 5. So we've got 5 over 5, which just comes out to 1. Choice C. For this problem, we have this x minus 1 over 1 minus 1 over x crazy-looking complex function. We want to know if we take the limit as x approaches 1 of this thing, which of these expressions is equivalent. And the reason they might care is if you actually plug 1 in, you end up getting 0 over 0. So they want us to do some kind of algebraic manipulation to get rid of that problem. So we're going to start by simplifying this complex fraction. And to begin that process, it'd be nice if I had just a single fraction in the denominator, so I could multiply by the reciprocal. So instead of writing 1 minus 1 over x, I could think of this as x over x minus 1 over x. And then I could just rewrite that as x minus 1 over x. Now that I've got just a single fraction down there, I can multiply by the reciprocal. So I have x upstairs. I still have this x minus 1 downstairs. There's an x minus 1 upstairs to go with the x. So this is the new situation I've got. And this is a nice situation because I can now cancel out those x minus 1s, leaving me with just limit as x approaches 1 of x. Now we could actually go one extra step and actually solve this. Take the limit, just plug in 1 for x, but they just wanted us to figure out the equivalent limit, which happens to be choice A. On this problem, we have the functions f and g such that limit at 4 for g is 7, and the limit of the quotient of f and g is pi. Based off this, we want to know what the limit of just the f of x function is at 4. So the key here is that if you're taking the limit of a quotient and you know both functions aren't 0, especially the denominator's not 0, you can think of this as just the limit of one function divided by the limit of the other function. So if we just take the limit of g of x as x approaches 4 and replace this g of x down here with it, we end up with limit of f of x as x approaches 4 over 7 equals pi. And now we're just solving for the limit of f of x as x approaches 4. That's just the numerator here. We can get that by itself just by multiplying 7 by both sides. So that's just going to be a value of 7 pi, which is choice C. For this problem, we're defining f of x as x minus 4 over radical x minus 2, and we want to know what limit as x approaches 4 of this thing is equivalent to. The reason they care is if you plug in 4 right away, you have 4 minus 4, which is 0, over square root of 4 is 2 minus 2, also 0, indeterminate. So they want us to rearrange this in a way that doesn't have that issue. Now the key on this with these radical and the denominator expressions is you have to rationalize the denominator, which you may or may not have done. The idea here, though, is that we want to multiply by basically whatever's in the denominator but the conjugate of that. So basically this stuff, but with a plus 2 instead of a minus 2. But we can't just do that in the denominator. We also have to do it in the numerator. So we're going to multiply this whole fraction then by radical x plus 2. In the numerator, nothing special happens. We just end up with parentheses x minus 4, parentheses radical x plus 2. But in the denominator, some mathemagic happens here. You basically have a minus b times a plus b, which is equivalent to a squared minus b squared. So radical x squared is just x. 2 squared is 4, so you basically have x minus 4 when you simplify the denominator. And that's a lot nicer to deal with. It also happens to cancel out with the x minus 4 in the numerator. So at the end of the day, this is equivalent to limit as x approaches 4 of just radical x plus 2. We could actually plug in 4 to evaluate the limit, but we just needed to match it with the correct expression, which we see in choice B. On this problem, we're defining the function h as x squared minus 9 over x minus 4. We want to know which statement's true. So these are all statements in which we're taking the left and the right side limit of 4. They have all that in common. And you'll notice that you always end up with either a negative infinity or a positive infinity when you do this. So clearly there is a vertical asymptote at x equals 4. And really all they want us to do on this problem is figure out what direction we're going, either up forever or down forever, as we approach this asymptote from the left and then the right. To figure this out, we just need to test x values that are really close to that asymptote. For example, the x value 3.9. If I plug 3.9 in here, I've got something that's bigger than 3 that I'm squaring, and then I'm subtracting 9, so my numerator is going to come out positive. Really, I'm just doing sign analysis here. So if we have a positive numerator, and then 3.9, or really anything less than 4 minus 4, is going to come out to a negative denominator, that whole result, positive over negative, is going to be a negative. And that means that I'm approaching negative infinity as I approach 4 from the left side. And if you weren't really convinced about this, maybe you think something happens in between 3.9 and 4 that alters this, feel free to plug in closer numbers. You'll see if you plug in 3.99999 as far as you want to go, you're still going to end up with a positive over a negative. All right, let's keep going. Let's see what happens as we approach from the right side, because this narrows it down to 2 answer choices, choices A and C. But we still have to figure out, am I going up or down forever from the right side? So I'm going to plug in something very close to x equals 4 into my function to see if I get a positive or negative. Now, on paper here, I'm writing 4.1, but the analysis we're about to do also applies to really anything bigger than 4, such as 4.000001 and as far out as you want to go. So you take one of those numbers, square it, and subtract 9, you're still getting a positive. If you subtract 4 from it, you're also going to get a positive, which means positive over positive is a positive overall result. So that means that we must be approaching positive infinity as we approach x equals 4 from the right side. So we're going negative, then positive. Looking at my answer choices, negative, positive infinity is choice C. On this problem, I'm taking the limit as x approaches 0 of this rational function. Now this looks pretty crazy, but you can see right away if you just try plugging in 0, since everything has an x, it's going to all get zeroed out and you end up with 0 over 0, which is bad news. So instead of doing that, we're actually going to try factoring first and canceling out a common factor. Since these all have x's, we can factor an x out of both the numerator and the denominator. In the numerator, I'll have x parentheses 5x to the 4th plus 3x plus 18. Denominator, I'm going to have x times parentheses 3x to the 4th plus 6. Now I can cancel those x's, leaving me with just whatever was in these parentheses is my only fraction now. At this point, now that I've canceled out these x's, if I plug in 0, I'm not going to get 0 over 0 anymore. But let me try plugging it in and seeing what I do get. So anything with an x is going to get zeroed out. I end up with just 18 over 6, which I can reduce to 3, giving me choice C. For this problem, we're told that we have this function f that's a function of x, and they're saying the limit as x approaches a of f of x can be found using the squeeze theorem with g and h. They want a graphical representation of this mathematical happiness. So basically, we want to see the squeeze theorem in action. The squeeze theorem essentially says that if you have a function that is between two other functions, and those other functions have the same limit, then your original function shares that limit as well. You're basically squeezing this function so that it can only have one possible limit which matches these other limits. So let's look at all of these things. In order for this to actually work, your f function is going to have to be between the g and the h function, at least close to a. Not necessarily all the time, but as we get closer to a, we expect to see f between g and h. So let's look at our answer choices and see which ones actually do that. Choice A, the f function, which is this bolded one, it's nice of them to make it a different type of line. It's going all over the place. It's definitely not between g and h, especially not as you get closer to a. The point x equals a. So choice A is no good. Choice B is not so bad as you come from the left side. F is staying happily between g and h. But once you get past x equals a, you can see the bold line here, f starts to veer off, and it's no longer in between. If you don't have this in-between action coming from both sides, then you're not going to be able to use the sandwich theorem, the squeeze theorem. So choice B is also no good. Choice C looks kind of suspicious, but it doesn't violate this condition. F is between g and h in this answer choice. So we'll hang on to this one for a little bit, even though it looks kind of sketchy. Choice D, f is definitely between g and h as you come from the left and from the right. So D is kind of the poster child for this, but we can at least eliminate A and B. Now we have to choose between C and D. Now the other condition of your squeeze theorem is that g and h have to have the same limit at the x value in question. We need those limits to match. Otherwise, we can't really pin down what the limit of f should be, other than the fact that it should be between whatever these two limits are. To make it a specific number, though, these two limits have to be exactly the same. So that means that choice C, which looked kind of suspicious, is no good. I mean, we know that the limit of f is somewhere between the limit of g and the limit of h, but we can't get a specific number because they are different limits. So we can eliminate C then. The squeeze theorem's not going to help us in this situation, so then only choice D is going to illustrate the squeeze theorem. On this problem, we're given the g function as 1 over this quadratic here. H is an even crazier looking rational function. And then they're telling us f is a function that satisfies g less than f less than h. So basically the f function is between or equal to g and h between the x values 0 and 5. Based off of all of this, we want the limit as x approaches 2 of f of x. Now this is kind of suspicious because they didn't give us an algebraic formula for f. They just told us it's between g and h, which they did give us formulas for. So really our only shot here is to figure out what the limit at x approaching 2 is for g and h, and then hope that gives us some clarity on f, which we know is at least between those two numbers. So let's try limit as x approaches 2 of g of x to start off with here. So that's 1 over all this stuff with 2 plugged in. So we've got, let's see here, 4 minus 8 is negative 4, plus 5 is positive 1. So 1 over 1 is just 1 for that limit. Now let's see what the limit at 2 is for h. So here is the h function with 2 plugged in everywhere. In the numerator, I've got, let's see here, this is 8 minus 16 is negative 8, plus 10 is 2. Denominator, we've got 4 minus 8 is negative 2. No, negative 4. So 4 minus 8 is negative 4, plus 6 is 2. There we go. I was just thinking ahead here. So 2 over 2 then comes out to 1. Well, since these limits are exactly the same, that means by the squeeze theorem, limit as x approaches 2 of f of x also has to be 1. Basically, since we're guaranteed f is between these two functions on an interval that this x equals 2 is on, and these two limits are exactly the same, f has no choice but to have that limit as well, because it's got to be between or equal to these two functions. So that ends up giving us choice B. On this one, we're told that function f is defined for x between 3 and 6, and which statement, if true, would imply that the limit as x approached 5 was 12 for the f function. Okay, so first let's just go through and see if we can eliminate some things. So there exists a function g such that f is less than g on 3 to 6, and the limit of g is 12. So basically they're saying this f function is less than or equal to g on this interval, and the limit of g is 12. Well, that doesn't mean that f has to have a limit of 12 at x equals 5. F could be much, much lower than g and still meet these conditions. So it can't be choice A. Choice B is also suspect. We're just reversing which one is higher up. If f is bigger than g and g has a limit of 12, well, that just is telling us that at that exact value, f can't have anything less than 12. It could still have something bigger than 12, though, like 13 or million. So let's move on to the next choice here. There exists functions g and h such that g less than f less than h, and we've got limit of g is 11, limit of h is 13. Okay, well now this is a little bit more intuitive here. So we're saying that f is between these two functions. One function has a limit of 11, the other has a limit of 13. Does that mean that f, which is between these two limits, has to have a limit of 12? Well, it means it could have a limit of 12. It doesn't mean it has to, though. It just means that the limit of f has to be between 11 and 13. But, I mean, that could be 11.1 or 12.999 or anything in between there. So this doesn't narrow us down to 12, although it's better than the first two answer choices. So let's look at the last one. We've got g and h again. F is still between them. This is good. And then they're saying that the limit of g and h are both 12. Well, now we're talking. If f is between g and h, and both g and h are approaching 12 at the same x value, then at that x value, by the squeeze theorem, f must also be approaching 12. So D is the answer choice we're looking for on this one.